Okay, welcome back to old school coding. So, good lunch. And we're back to working on the clock stuff again. So we have now the ability to initialize our clock. Initialize our clock to a specific clock frequency. We will assume that the tau value is going up at that hertz. So that represents a rising and a falling edge on the primary oscillator. So what we'll do is we're going to have this convention that I'm going to have a global signal called clock, which people can subscribe to. And I will send out a rising edge and I will send out a falling edge. And then I will advance the time. Or actually, I'm going to advance the time and then send out a rising and falling edge. And I would normally, if I weren't worried about time, I would use the scheduler for this. So the clock would schedule its rising and falling edge, and then it would run, and at the end of its run, it would schedule another. But looping through the scheduler costs us time. We can see here that this is, it's a time that increases as we get more and more things on the schedule. Now, at some point, we may have a system with multiple independent clocks with independent frequencies. For instance, if I were to try to simulate the CPU board of a Sun 4600 series machine, potentially we have a primary clock from the motherboard, which is the M-bus clock, and then each CPU module has its own independent clock, which is not at the same frequency even nominally. That would be a kind of a difficult one. I would need to get some documentation that I don't believe has ever appeared in public and was hardly ever looked at in private, aside from the guys that worked on that bit of code, to do a decent job of synchronizing the CPU at one frequency with the M-bus clock at another. It's not hard, it's just tricky. So what we have right now is a global clock. We have the ability to initialize it, and we have the ability to say, if I have two tau values, how many nanoseconds is between the two? And that's kind of the start of the time base. But the next thing is I need an edge that I can wiggle. Well, you'll notice that I've got my display properly set so that the text should look good. My preview in OBS, of course, is scaled, so I cannot tell what scaling is happening on YouTube. But at least I'm not doing a transform from up by 10% or anything. Decided to take a little bit of time to look up the keyboard commands and configure my system appropriately. I haven't done a whole lot of development on this particular Linux image, so this is why it wasn't configured. Anyway, so let's see here. I need a edge. We're going to include edge.h at the top. And we're going to need it over here because anybody that looks at clock is also going to get this extern edge. And I'm going to put this all in uppercase because when you look at schematics and timing diagrams and such, signal names pretty much always look uppercase, and I'm going to try to write my code in the language of the problem domain, which is a modern way of putting it. The old way of putting it was make the code match the design documents. Thank you. So we have edge clock, and that's going to be just like, put it up at the top there. Okay. It's not extern. So this will initialize clock. And clock will have all of these values associated with it. And I need to call an initialization thing. So we're going to do that here. Edge init clock. So if you don't call clock init, edge is not going to be initialized and you won't be able to do anything. Now, edge invar, I'm going to do a We do edge invar on clock as part of clock invar. Clock init, clock invar, assert. So at this point, we should be coming through here. I'm going to put a printf in here so I can verify what's going on. And yet we're calling clock invar in several places. Good. Now, I really want to make sure that I actually have a clock frequency. Clock frequency of 0 would be very bad. So I'm going to say assert create that integer 0. And I really don't care. If somebody wants to run their 8080 with a primary clock frequency of 1 hertz, that's fine. But it does need to be non-zero, which means I need to go in here and say assert clock hertz greater than 0. So we will reject any attempt to initialize us, but we'll also set that up as an invariant. So I should have thought of that. The moment I wrote this divide, I should have put a protection against negative and 0 values. So I could do all sorts of fancy things and have clock methods that proxy into edge methods, but I think if I'm advertising that I have an edge called clock, I think everybody else can just say, I'm going to use the global clock signal. I want to subscribe to the global clock signal. I'm going to treat it as an edge. They don't have to go through the clock package to get to it. It's there. I'm exporting it. However, I do need a clock step and a clock loop. So void clock step, I call it run 1, and void clock run, how about run until? So we'll have a defined exit point. If we do run until, I'm going to say run until, I'm going to give it a tau value. Tau, and we're going to stop. If we step forward until we reach that tau value, we'll execute the clock edges for that tau value. But we won't go beyond that. So I'm going to call this last. Clock.h. So people can opt to run the clock by 1 step and get control back and do something else. Knowing that running the clock is going to increment tau. Or I can do a run until. So if we're running until, this is going to be real simple. While tau is less than last, clock run once. That's super simple. Clock run once, we're going to tau plus plus. We are going to clock edge high on clock. So we get a rising edge on the clock and a falling edge on clock. We do not step forward by tau between. If I did that, okay, this is a valid way of doing things, and it would allow me to have some things triggered on the falling edge of clock. It would also mean that if I'm storing data about a signal, we've got the current tau and we've got the, so we have it, yeah. That actually, if we ended up printing 1 character per tau, I'm thinking ahead how we're going to display signals. I can show a low, I can show a high, I can show low to high, I can show high to low. There's no real good ASCII character for high value. I'm going to use a tilde. So we might get a clock signal that looks like this. So potentially, if we've got such a thing as a tri-state, we'd have tri-state there. Then we might have a goes high. And then we'd have, it might be high for, whoop, tilde is not a good value. Let's use up arrow for being high, and then we might go low, and we might use an underbar. So our clock might look like that. And some other signal might look like so our ligatures are doing me dirty here. Dash, dash becomes a longer dash. So the clock signal might look like that, because it's going up and down once per U. Now, if we've got a multi-phase clock coming in for the 8080, it might look something like this. We might rise, rising edge, falling edge. Might have a rising edge there. Okay. Instead of drawing this out, I'm going to talk it out because there's a cat that wants to talk with you. Hey now. Okay, you saw the characters I was using for the, representing a signal high, low, transition, and so on. Currently, Edge doesn't have a notion of when a signal is tri-stated. We may add that at some point. I just realized that there is no call you can make into Edge to ask it what the value is. You have to actually just peek at the value. I should probably have a macro to do that. For now, we can just use it. So the thinking is that if I have a tau for the time at which the primary oscillator is rising, separate from when it's falling, that means if I got another signal at half that frequency, it would show a rise in one character location, and that would show high. Then it would show as falling, and it would show low, and so on. And that's actually fairly clean. So I'm going to do that. I'm going to have tau increment by 2. Which means that tau is incrementing by 2 for each clock cycle, so my math has to change. So if 2 for clock cycle, return time is ns, frequency is in hertz, this is in 2 times tau divided by s. So elapsed time is times 0.5, actually. There. And now, this is, I'm going to be incrementing tau twice, so that should be the right numbers now. Clock run 1. Okay, so that works. So for an 18 megahertz clock, we increment tau by 36 times per microsecond. That means that 2 microseconds is 72 tau. Well, 72 columns of text happens to fit very nicely in a terminal. And that, 2 microseconds, is an instruction time on a 8080 CPU. So this scaling of values will look good for the target that we are doing, and it is something where we can change it. You can ask for a different clock frequency. You just have to know that tau is incremented by twice for each clock. So we have the ability to do things. I can, in theory, somebody could subscribe to the descending edge of the primary clock if they wanted, or the rising edge. Either way, And the only cost we are paying is that we are incrementing tau twice. So that needs a test. So power on self-test. The first, what's going on with my keyboard? So the little rubber thingy is, so this keyboard has these little legs that go in magnetically, and they've got rubberized bottoms. And it has been a lot of years of service, and the rubberized bottoms are not sticking so well. I think I may have peeled them off at one point. I'm that kind of person. This is a drop CTRL keyboard, and I just love it. Got nice switches. Feels very good under my fingers. People talk about how they sound. Oh, I'm not much into the sound, but I'm very much into, I need it to feel right. I need to have tactile feedback as I type. Anyway, undigressing. Need to test it. So we've already checked here that this does the right thing. And now I'm going to actually run this by going tau t0 is equal to tau, and then we are going to clock run 1, t0 plus 2 is the expected value, and tau. So we're going to say run 1 will increment tau by 2. And we're going to say run clock, run until t0 plus 72. Okay. And that appears to be running. If I change this to 71, I do indeed get an abort with a failure on that test. Notice I am not jamming a value in tau. This is an agreement I'm going to have to make across the system, is that jamming a value into tau that isn't based on a previous tau value is bad juju. We do not ever want it to go in reverse order. I would much prefer always incrementing, which is one reason why I don't like that I keep coming back to this, step at. I do not like the fact that step at is writing into tau here. I really don't. No, I really, really don't like it. At some point, I'm going to have to do that. I tried earlier today to eliminate that and to fix up the tests that depended on it. And just, oh, good God. So step at always writes. Sched checks versus tau and assumes tau is updating by sched at. There's nothing that says that sched really has to have tau changing. This is all just maintaining tau. And that write of tau, updating tau takes time. Okay? But notice here, sched inc repeat. Okay, sched absolutely has to have the time update before the function call is made. Otherwise, the function won't have a tau value it can use. So our alternatives are to never have sched loop. In other words, sched would be called with tau set appropriately for its first job, and it would execute the first job, which had the appropriate tau, and then it would return. That limits the scope of sched significantly from what I wanted. So yes, I guess sched has to update tau, and the easiest way to get that done is to have step at update tau. God, I keep working my way through that and coming back to, nope, step at has to update tau. So here's how we generate this clock. Now, at some point, in an outer loop somewhere where we're doing things, I'm going to have to say, as we're running our clock, sometimes we have to go do the sched stuff. And I think that has to happen in clock run 1. I wish it didn't. So if we didn't want to do it in clock run 1 inside the inner loop, what we do instead is adjust the run until so that instead of tau less than last, before we do that, we'd say if there's something on a primary schedule, we don't have a singleton schedule yet, so we can't do this yet, but thinking out loud, we would have a primary singleton schedule that says, here's globally things that are needed to be done, and a singleton FIFO that says, do these before you do any more clock edges. So our loop becomes trigger the clock, trigger the stuff on the singleton FIFO, okay, until it's empty, and then go out and look at the next schedule item, and we need to make sure that we run clock FIFO, clock FIFO, clock FIFO, and we stop and go do the sched thing when we arrive at the time of a scheduled item. So when we build our singleton schedule and our singleton FIFO, we'll have to hook that inside the clock run until, so that it knows to do run 1. Run 1 is, this is time critical. Time critical things, as long as the condition test to do them is minimal cost. Clock elapsed NS. I am not going to call this time critical. I do not believe anybody that's simulating things is going to be saying clock elapsed NS. I do believe that if we're monitoring signals for, is this signal staying high enough, or is the time between this signal going high and this signal going low between 120 and 240 nanoseconds? So if we're doing that, we're not running time critical. But yeah, clock run 1 and the loop here have to be there. Now, it is possible that during any given edge surface, okay, somebody could schedule something to happen in the very near future. I am inclined to disrecommend the use of schedule to try to schedule something within the next few clocks. Again, something to bear in mind when we get to our global thing. But popping our stack, ignoring the singleton schedule and the singleton FIFO, we are running until a tau. That's fine. We're not going to have a run forever because the simulation has to have a bounded run. There is no case where I want the simulation to run literally forever. Even interactive session, I think overall, if I'm going to be simulating an actual CPU system, what I want to do is do a clock run until for some big chunk of time, okay? And then I want to back out and check things. For instance, I want to have an opportunity. Maybe I'll run 1/10 of a second and then check the status of a simulated front panel. Maybe I'll run a millisecond and check the status of some simulated devices. Maybe there's a simulated disk drive that wakes up 60 times per second and may or may not deliver me a sector. I will have to look up timing of the old floppy drives. How fast did a 5-inch floppy spin? Oh, that's a good question. I'm curious about that. I'm going to look that up right now. How fast did a 5.25-inch floppy disk spin? Okay, so rotational nature of the floppy disk, rotated at 300 RPMs or 5 times per second. So at most you could read 5 tracks per second. That's it. So 5 tracks per second on an 8-inch flop, on a 5.25-inch floppy. 8-inch floppies, which are older technology, retrocomputing.de says that floppy drives ran from 300 to 360 RPM, depending on the disk drive. So 5 or 6 revolutions per second is about it. And this is not going to be consistent. And in some systems, maybe the clock speed was a bit variable. Apple was famous for doing this to great effect. You can store more data on outer tracks because they are longer. So you spin the drive faster for inner tracks and slower for outer tracks, getting the same bit density. A really cool idea happened with the Macintosh. I'm not simulating a Macintosh. So the here on the records, there's the fastest rotational speed for a floppy disk was 1,440 RPMs, and the equipment could write both sides of the disk at the same time. So, yeah, when we start building our floppy stuff, those are the kinds of numbers we'll look at. But this means that we would run the system clock here. We'd dive into this loop for some rather long time that we are going to compute in the simulation that calls clock run until. That says, I have a physical system. The next important physical thing is going to happen this far in the future. Well, this far in the future means I need something. I am going to need the reverse of clock, elapsed ns. I need to say extern tau clock ns to tau. Okay. So, let's see, how about I just do clock at future, I'll call it clock future tau. So if we have something that's this many nanoseconds in the future, what is the future tau? So it'd be current tau plus this many nanoseconds. And in the spirit of every sleep command that has ever appeared in any Unix or Unix-like system, I'm going to say this is this many nanoseconds or more. So really, clock future tau. Okay. So this is going to be, I'm solving this equation for end tau, given a start tau of that. So do this the easy way. We are going to times 2 times clock frequency hertz divided by ns per second. And we're going to add tau to both sides. And there's end tau. So what are the chances we would overflow a 64-bit value here? If delta ns is too huge, we might. So as part of my post, I want to calibrate, actually as part of BIST, I want to calibrate how big delta ns can go before clock future tau wraps around. Well, that's not a bad idea to have in hand. In fact, I am going to end minus start, like that. These are simple, and there is no need to break them down and make them look more complicated than they are. So now we have a clock run until tau TF is equal to clock future tau of, say, I want to run for a millisecond, like that. I'm going to have tau expected ns equals this. I'd really like to write this all in one line. So, and the final thing is tau observed ns is equal to clock elapsed I'm going to reset T0. We're going to be messing with T0 a few times here, so let's make it a thing like that. Okay. So I'm going to make it so that the output message from here is useful. So we're going to say clock future tau of expected ns. We're going to pass that to elapsed ns from tau. That's going to be equal to that. And what errors do we have? Okay, so expected ns undeclared. So I left this with a failure in the test, didn't I? There we go. So now if I change that, we now get a failure. Oh, I didn't look carefully at what the failure message looked like. Failure message says, test condition failed, clock elapsed ns of future tau of expected ns is equal to and I wanted to put the expected value on the left in that print, didn't I? And I guess I rolled back that change, and let's make it right. Oh, haha. Good thing I did roll it back, because expected less than observed. Actually, assert op. Okay, assert less than integer. Expected 0. So observed less than observed less than expected is the way this should be written inside here. And it is indeed observed op expected, observed op. So I need to have observed on the left of this print. Otherwise, I need to reverse the operator. And if I'm past a string that says less than, I can't really reverse that. So that's correct. So these messages will have the observed and expected in that order. There. So this says that if I compute a future tau and I check the elapsed time, it comes back with the right value. I was going to assure that it rounded up. So for future tau, I'm going to say plus ns per sec minus 1. So if it's 1 nanosecond less than hitting the next thing, we're there. So now if I do this again, one nanosecond less, so I still need to put 1,000,000 in here for the expected value, but I'm going to say expected ns minus 1. If expected ns is a multiple of the clock period, then elapsed ns returns the original ns. If expected, if the, let's do input ns and expected ns. No. So I'm thinking one weakness here. No, is this right? Is this right? Should be right. Right. I am multiplying by the clock frequency, which is like dividing by the clock period, and I'm doing the right thing to cause it to be an integer. So we're there. Now if I do plus 1, so notice my observed value here is, because I incremented my desired delay by 1 nanosecond, my actual elapsed delay for that number of tau is going to be 27 nanoseconds beyond that. So we don't round up to the next ns, next tau counter, which So this is going to be, I better not call this expected. Call it nominal. Now, I'm not changing nominal. So this test now requires 18 megahertz. So if the default changes, we're still going to have to run 18 megahertz here. The other way to do this so clock period NS will be the period of the clock rounded down. So now we need to make sure that the period also is greater than 0. So stub percent 15 LLD clock frequency hertz. Going to print it out in megahertz as well. So this says initializer element is not constant, ns per second. Well, that's bull crap because this is a static constant, so we're going to do pound define instead. Keep forgetting that old C has some notions about constants. Initializer element is not. Why would it think that's not constant? And why is my build not building? Interesting. So that's a weird thing. So what I'm going to do is I'm going to now say that you have to call the initializer for this to work properly. Our invariant will fail if you don't initialize the clock. Little name change. It's no longer a default, it's just a standard. Okay, so now we're going to print this. Clock frequency hertz, 18 million. Frequency is 18.0 megahertz. Clock period is 55. Period is 0.055 in microseconds. So clock period is rounded down correctly. We are going to not print that from now on. I am going to continue to do these things. Actually, instead of dividing by clock frequency hertz, I think I can take end minus start times clock period ns. Oh, nope, that's not going to be accurate because this is an estimate. Period is only approximate. So period is really only for a few things. For instance, this is going to be clock period ns over 2, no, times 2. Yeah, over 2, over 2. That works. But notice that when we have larger and larger spans here, multiplying it by the period will be less than our actual time because our clock frequency hertz is primary. With that in mind, why are we even storing period? Let's create it here where we need it. Yeah. If it can't be done accurately, it shouldn't be done. So the expected value was 55. Actual value was 27. We need to divide that again by 2. So clock elapsed ns does round down. Okay, so if it's 55.55, it's going to give you 55. Integer math for the win. And clock future tau does round up. So instead of 1.11 units, you're going to get 1.2 units. So all these rounding things are in the correct direction for what I want to do here. let me write this up more specific. Clock future tau rounds up when the desired ns is not a multiple of. When the actual clock frequency got that backwards. So I am trying to write this clearly, starting with what clock future tau does. So clock future tau takes a nominal number of nanoseconds and computes the number of half period times rounding up it. So for 18, where okay, so future tau takes the number of nanoseconds. So if we asked for 50 nanoseconds, it would return 2 cycles. You know what? Having written that out that way, it's probably what I should test. Now the other one is clock elapsed ns takes a starting and ending number of half period times and returns the number of nanoseconds they span. So I could round down or I could round up. I think I'm going to round down. So I'm rounding down here. So if I take that result and I pass it back through clock future tau, it rounds up. So that if the result is passed back through clock future tau, we get the same number of half period cycles back that we originally That's a separate test. Okay, so if we take a number of cycles of half, calling these half period times, convert to ns, then convert back to a future tau, the delta tau we get out is the value we put in. I'm just correct change in tau we get out. Okay. So now that I have expressed in English what it does, we can test that it does what I have expressed in English. So take a nominal number of nanoseconds and computes the number of half-period times. So we're going to say assert EQ integer. So if we ask for 50 nanoseconds, we should return 2 cycles. So we're going to say 2 is equal to clock future tau of 50 minus tau. Nominal ns isn't used. Nice clean thing. Okay, so for starting and ending number of half period times, it returns the number of seconds. If we add as the above sample, if we ask for the elapsed ns for 2 half period times, which is 55.5 ns, then we get the 55 ns as the result. Say tau minus 2 to tau. Generally, we will be checking elapsed times of things in the past, from a past point to the current point, or from an older past point to a more recent past point. So if we convert to nanoseconds using this, and then we convert back, we should get the same thing. And that should be true for any value of 2. So int is a tau hpt is equal to, I'm going to start from 0, This is more of a BIST than a post, but we'll move that later. So we take this whole thing now. This becomes BIST. I'm going to beef it up some in BIST, and then I'm going to prune it back some for post. We'll still do those two, but here we're only going to do 2 examples. Let's add tau to both sides to maybe make this work a little better. How about 220 and 200? You know what would be cool is if I could turn on something that had this assert print out its error message for a pass. But for now, let's just take a look. So the error message, if I'm off here, so where expected value is, we should be getting 225. Okay. No, I really want to see the delta here, not. So I do need minus tau. How can I keep this from being an extraordinarily long line? I think like this. So, what am I actually returning for these things? I'm actually returning 20 and 200. So the elapsed nanoseconds for this is going to be more decimal points. So we have 55 blank, and then 55, 555, and then 5,555, and so on. But let's assert that. So as we add more zeros, we are getting better precision, relatively. We're still, 1 nanosecond precision, but it is taking it into account. It isn't just multiplying 55 by that. There we go. And my indent did bring that up like that, and I think it's going to complain if I try to do this. Yep, it's breaking the line. So I'm going to tweak indent to be a little bit longer lines. Can I do that? Can I go to 96? Yes, I can. There's probably a bunch of other files that are going to get reindented. Let's take a look. Get diff -w into cat. So we changed indent.pro. We add clock. Okay, I like what this does. It's bringing a lot of lines up to single lines that were double lines. I just need to make sure to comment in the commit that I did do a reindent, which is why so many files were hit. Okay, so now we have working future tau and elapsed ns, and that was called all kind of a yak shaving diversion because I needed to add this future tau along with elapsed ns. Let's update this, and we still want to run this for a whole bunch of things. Let's run it all the way up to 1,000. Okay, so built-in self-test is going to test that this holds for all futures, all values of HPT, all the way up to 1,000 nanoseconds. I could run it up to a milli. This is like a really thorough overkill test, and it still runs so fast, it's ridiculous. And I'm going to just verify. Yes, we are getting to the end of the test here. So that's still just testing the math. We have not tested run one or run until to any solid extent. I mean, we've run here, we've run here. Do I want to test any further? You know, I think I need to do, though. Oh, do we use T0 anywhere here? We do not use T0 below here. I'm going to check the math before I run that stuff. So we're going to do 0, we're going to do 72, we're going to do T0, run until, and I'm going to use clock future tau of some nanosecond time, 1,000,000. So we're going to run for a millisecond. Now, instead of comparing tau, this is going to be assert EQ. So having run that, we're going to assert that it is equal to this long run ns. We're going to run for 1,000,000 nanoseconds of simulated time, and we're going to assert that it's equal because we can use EQ here because I'm a fool. Long run ns is what's desired. Int long run tau, these are all tau, and tau is equal to I think what I'm testing here is a tautology, but we'll go with it. This is going to be clock future tau of long run ns. Tau, so my expected tau is going to be tau long run end tau, which is going to be expected tau. Expected. Now, expected ns is going to be long run ns converted done to the math. I am going to make sure. I'm just going to do. Okay, yeah, I'm going to have to assume it's a. Yeah. So, note for this to work. long run ns must be a proper multiple of the actual real period of the clock. At not a multiple of the rounded down period. So we're actually going to run the clock until then, and then we're going to observe the result rather than simply computing where we think we're going to end. Kind of a verify things without doing the math. We're going to say run for this long. Now, clock bench is even simpler. We are going to init. We are going to, and we're going to benchmark something that does a clock run until of, So our benchmark function is going to look weird. So void bench clock of some pointer. So let's see, tau t0 equals tau. Okay, so bench clock runs a bunch of ticks. And we're going to say static tau bench delta tau is equal to 0. We're going to store tau minus t0. Actually do bench start tau and bench end tau. There we go. Just going to double check. I haven't been monitoring my live streaming, which means maybe somebody was chatting and I didn't see it. I think I've got chat turned off. Oh, bugger. Apologies to anybody. No, live chat's turned on. Okay, there it is. Part of my window was obscured there. Now I see it. Okay, so nobody's been actually viewing this so far. We'll see what comments come up when people look at it later. That's the problem with doing this during the working day, is most of my friends work and nobody can look at it. So, benchmarking. Use the following macro, RTC elapsed of bench clock, and this is ns per clock iter. Ns per clock for 1 ms is just dt, and we'll see what that comes up with. So this guy wants to have a pointer argument of some sort. Clock bench is probably not being called by main. Oh, there it is. So this is saying that I am taking 85,000 milliseconds to do a call to bench clock. That's fine. So this is ns per clock cycle. This is really ns per clock run 1. dt over student bench start final tau minus bench start tau. Tau increments by twice per thing, so we want to times 2.0. There we go. So clock run 1 takes about 5 nanoseconds of real time to run. And that's when when there's nothing on the queue for it to run. And I am going to, let's do it with various numbers of things on the queue. So the first DT is going to be with nothing on the queue. Then we are going to put something on the rising edge. So static void tick So edge, hold on, bring up the API to make sure it's there. So edge on rise of clock, please call tick with ticks as the parameter. Ticks is an array. This is tau, counter, so if we put something on tick, I'm going to do another bench val. So the first number is going to be no clients. Second number is with a tick. Come on, ticks becomes tick count. Tick becomes, oops. I'm just going to turn this into an inc function. We're going to have a tick count. We're going to have a talk count. So now we have 3 numbers. So 4.8 with nothing, 5.8 we've got a tick count, and 6.6 we've got a talk count. And I'm going to add, so we will have 10 tick counts and 1 talk count. So if we've got 10 people listening to the ticks and 1 listening to talks, then we've got that. So also what I'm going to do is I'm going to divide this further by instead of these, I'm going to divide by tick count plus talk count. So these numbers will be cost per call to the endpoint thing. And that means I do need to reset tick count, talk count. Oh, but if this runs this multiple times, yeah, okay, so I will have to set these in bench clock. There we go. So when we start the bench run, it clears them. So when we get out of this, it'll be the counts for the final pass through it. Okay, so amortized cost for each call to a guy that consumes the clock. 4.6 if we've only got one, goes up to 4.6 if we've got nobody. That's the total. That's the non-amortized cost. If we add somebody, that means it's 5.7 per call to tick, if that's only a thing there. If we have a tick and a talk, they take 3.4 nanoseconds each. If we have a whole slew of ticks, they take 2. For int subs equals 1. We had 1, subs less than 10 plus subs. Actually, while clock arrow, take a look at edge again, arrow rise, arrow length is less than 10. Do that. Then we're going to do it again with 100, and then we're going to do it with fall. So this is going to show raw cost of it, and then as we go out here, the cost as we add more clients. And these took longer to run than I like, so what we're going to do is inside bench clock, I'm not going to run it quite as long. So this could be 100 milliseconds instead of, 100 microseconds instead of the other one. Okay, that still runs fairly fast. I think I can still get precision running only for 10 microseconds. That's good. So you see, as we have more and more people listening, the amortized cost of each one of those calls drops to 2.3 nanoseconds per, which is competitive with running in subs, which is good because this is a subs. There's a little bit of extra overhead, but that's okay. Oh, that's also because the thing I am calling is doing real work. I believe subs, was I incrementing? Let's take a look at the subs benchmark real quick. So yeah, the subs bench was in fact doing an elapsed time of subs run which calls the whole thing. And what was on the list was subs fn1, which increments something by 1. So it's the equivalent thing, so we take a little bit longer if we're inside the clock to do the whole clock thing, bumping it up, bumping it down. So updating tau costs us time, but we have to do it because it's, it's what's there. I think that gets us our clock system running. We are basically quiet. We are printing out our benchmark results. We have no BIST failures. We have no post failures. We are good. Okay, so that was an hour and a half to turn out what was probably on the order of maybe an hour worth of work in the real life. Again, this is something you would have taken care to do carefully. It is likely that instead of building up all of the smaller things, if I was doing this, let's say I was at Sun in 1992, I was, but let's say we're back in that mind frame and I needed to write this simulation module. I needed a clock that wiggled an edge. I would have dove straight in with in parallel clocking, writing edge and clock in parallel side by side. And a lot of this stuff wouldn't have gotten done. Some of it would have gotten done later. The only tests that would have been written would have been the functional tests for clock and the functional tests for edge. a lot of the smaller fundamental building blocks simply would have been skipped over. And the reason why I did them this time was I wanted to exercise through the processes, because it's been a long time since I've done things at this level with these particular ways of doing things. And I wanted to make sure I had that locked down before I got into anything more complicated. And edge and clock are beginning to move in that direction. You'll see bigger things coming up shortly. So now that we've got our clock, what do we want to do next? Well, this is a oscillator at a constant frequency, which is really great if you're doing a spark or an arm or a Z80, which takes a single phase square wave clock coming in. We're aiming at doing the 8080, which is much more complicated. So I think at this point we are going to start moving towards items that are specific to the system we're going to simulate. I'll update my, down the lower left I've got my README file. It's an org file. I've collapsed it to just the outline. I can see there, if I move my name, okay, so you can see what outline I've got here. Talking about subs, FIFO, SCED, and main. So I will need to update this, just talk about clock and how it works. The interaction between clocking up to a given tau and what we're going to do with a global singleton FIFO and a global singleton schedule, which we will not add until the simulation we are building requires it. That interaction is going to be interesting. Clock run 1 will need to run the global singleton FIFO. And clock run until will need to stop when it's time to run the next event from the global singleton schedule, which we hope the global singleton schedule is few and far between. And of course, the simulation itself, which is going to be calling in to run until, will handle running until the next interesting outside world thing, like input has arrived or data is starting to arrive from a disk drive, things like that. Data is starting to arrive from the computer network, which is probably going to be, I think, I think in the long run, I'm going to have some kind of networking on this box, even if it's only a dial-up modem. Let's say a modem that dials up and connects to some service that is willing to talk back and forth to it in some protocol. I don't know. Maybe I will resurrect the XNS protocol. Oh no. Or maybe we'll just have, a modem where we can start a text session with something on the other end, and some way in the simulation of saying, please connect this to a telnet port somewhere else. I think there are still telnet servers on the internet that do interesting things. What I'd like to do is maybe find a telnet port somewhere. Maybe somebody is still running a classic MUD on a telnet port. That would be really cool to simulate an 8080 dialing into a bulletin board system and running a MUD, telnet MUD. Can you play MUD over just SSH telnet? Okay. Yes, there are still MUDs out there. Holy Toledo. Yay. I hope what I'm seeing on the web are current things and not, 20-year-old talks about something that has died 10 years ago. But there's that potential, is that once we get our little 8080 system running, executing forth under CPM, maybe inside forth I can write a little telnet client, and we can use that, simulated 8080, we can simulate dialing into one of the MUDs running on telnet. Wouldn't that be cool? I think that would be awesome. Anyway, that's all for the future. I think our next session, we're going to start off looking at the 8080 documentation. Specifically, I'm going to start off with the clock generator chip. The processor really can't do much until we've got a decent clock coming in. I could start building up the processor, but it would be kind of untestable. We can't do the other parts of the system. We could do a memory, but again, we need clocks coming in. So we're going to start with the clock generator, and then probably the system control chips. So the 82, whatever it is, that generates memory read, memory write from the status bits that the CPU sends out. God knows why they didn't just do the right thing in the CPU. Maybe they didn't have enough gates. So there's a cluster of 3 chips: clock generator, system control chip, and the 8080, which form that chipset. And that starts swinging into the system we are building. So this is a transition from writing the simulation engine to writing the simulation. As we expand the simulation, we will be expanding the engine itself. Like I said, we don't have our singleton schedule or our singleton FIFO set up, and we're going to resist doing those. I would love to do an entire simulation that does everything edge-based, because those singletons are going to cost us. Every cycle we have to check those, potentially. Well, every cycle we have to check the FIFO. And whenever that schedule changes, we need to have something that says, oh no, we need to stop early because something's pending on the schedule. So that's this session. I'm not sure when I'll do the next session. I need to do some prep work. I need to pull the documents in from my archive. I need to check and make sure, well, first of all, do I want to publish those documents back out to my repo? Because it's a big size PDF. And secondly, if I want to do that, do I have the rights to do that? So these are documents that Intel used to charge $5 for in 1975. So they are almost 50-year-old documents that are almost certainly out of copyright. Intel is almost certainly willing to let me do this. I mean, even if it was 1980, I think Intel would be perfectly happy with people giving away copies of this document. I mean, their $5 was basically their cost of production and delivery, for goodness sakes. And they wanted people to use their chips. So it is likely that I have the right to publish, but I want to make sure. It is not so certain that I have the desire to place this in my repo, because it is a big PDF. And it means that when you clone it, you get this big blob, which is the PDF. It might be better if instead I include in my repo a link to the most official source for that document I can find. So I'm going to do some scouting around, and when we come back, we'll start talking about details of the 8080 multi-phase clock and how to generate it and how to interface with the control bus and what we're going to do for the design of the simulation of the CPU chip. I will see you then. So keep your code safe and keep it fast. I need to figure out a good tagline. Old school coding was all about, the code doing the right thing fast enough. And sometimes you sacrifice the right thing to be faster. Talk to Seymour Cray about that one. Yeah, sure, you don't need all those bits of precision. We'll just get you your floating point answers even faster if we can fudge the answers a little bit. Yeah, keep it.